Hey, it's me, and in this video I'm going to show you how to perform a power glitching attack to extract the firmware of a protected chip. The whole setup is built in a way that you can follow along even if you haven't done anything with power glitching yet, and it only costs around about 20 euros. I will show you the whole process, starting from soldering to programming and flashing the chip, building a power glitching circuit, and use a thermal camera with eye spray to explain how the attack works. A few years ago I had to use an FPGA and the Verilog language, which is quite hard to start with. But nowadays we can replicate all of this with the Raspberry Pi Pico and the PIO language, which is absolutely awesome, right? So the whole setup, it's also not a one-trick pony, you can replicate other glitches too. For example, I was able to reproduce the famous Apple AirTag glitch done by Thomas Roth, identified by limited results. And by the way, just beforehand, this doesn't work anymore, the vulnerability got fixed. But nevertheless, you can replicate other glitches with this setup too. So all you need to do is simply just watch this 1 hour video, and afterwards you will be able to start performing power glitches too. So therefore, let's get into it. Let's go.
Infinite cyber.
Our target board is the STM32F401 BlackPill board, and we can see we have to do some soldering first. So we place some crocodile clips on the pin header, which means we are getting a very good angle and they are not crooked afterwards. Say goodbye to crooked headers for good. Let's turn on the soldering iron and there we go. Oh, this is so satisfying to watch. We simply heat up the pin and then directly apply our solder onto the pin to melt it directly on this pin. This gives us a way better joint. Now it's time to clean it up. We use isopropyl alcohol to get rid of what's left on the board, and we do some visual inspection. I mean, look at this, no crooked headers, awesome. If you want to glitch the chip, we first have to program it. On the backside we can find the SWD pinout, which stands for Serial Wire Debug Protocol. It simply gives us access to the chip. Talking to this chip requires a programmer. We can use the top half of a nuclei board, a breakout board as a debugger, and here we can see the corresponding pins: clock, data I/O, ground and VCC. We could also use a cheap one from your vendor of choice with this corresponding layout, so I will go with the breakout board. We place our board into a breadboard and look at this, we can simply gently press it in. We now attach our debugger, in my case the breakout board, and here once again the pin out, that you do not mess up ground with VCC. This is very important. If we now connect to our debugger, we can see it immediately dumps the whole firmware. We can now extend this memory read and there we go. There's a blink LED example on it, which we are now flashing with our own custom firmware. So this has been done. This code opens a UART console which is password protected, and we can find the password in our unlocked chip right here. Our task will be to dump the firmware to extract the secret password, but I mean of course, not on an open mode like this. We are going to lock this chip in just a moment, but not yet. We first have to figure out how, and maybe even better, that everything works out as planned. The readout protection can be set under option bytes, and yes, it is simply just a byte consisting AA for no protection, BB, the firmware is protected but access to RAM is given, and CC, everything is protected. We can see right now it's AA, which means unprotected, and this is the mode we are using first to test everything out. Next we attach a power supply, which could be also done with the 3.3 voltage rail of the Pico, but during the glitching we want to have some kind of observation what's going on, and the ampere drained of this device is a very good indicator. If we start the power supply, we can see a blue LED lights up, it's not blinking anymore, which means our flashing was successful, and we drain round about 4 milliamps. Keep this in mind. Okay, now we want to glitch, and therefore we have to answer 3 questions. When do we need to glitch? How long do we need to glitch? And where do we need to glitch? 2 of them can be found in the datasheet. Crazy, right? And only the width of our glitch is something we have to simply try out. If we glitch too short, no effect. If we glitch too long, the board resets or even maybe breaks. But no worries. This timing can be easily observed with an oscilloscope, and it might be the same for your chip at home. So you can simply copy the script at the end and you should be absolutely good to go. So now let's focus on when and where to glitch, and therefore we have to pull out the datasheets. There are several different datasheets available, and guys, I really would like to show you all the cool stuff that's in there and how you could use this for an attack. But based on the potential overtime already, I guess we simply focus on these three things. So let's answer the question, when do we need to glitch? This answer can be found in the datasheet AN3155, which describes how to use the USART protocol in bootloader. It sounds, is this even correct English? Anyway, within the bootloader command we can see we've got a read memory command. This command has two perspectives. The host side, that's us, not interesting, but here, device side. This is how the board passes this command, and we can see awesome protection active. This means we've got a read memory command that checks if the protection is active, exactly the moment where we want to glitch. Okay, this was fast, so we might have missed a lot of other information. Let's get back to the beginning and then see how the interaction works. Point 1, USART bootloader code sequence. Let's see. Okay, the device side describes receiving a 0x7f, which means we have to send the 0x7f. We can also see we have to use an even parity, and if everything is correct, we get back an 0x79. The baud rate can be set to 115,200, and here we have a lot of different other commands. Let's focus on those two. The read memory command is, I guess, clear, but we also take a look into the get command because it is simple and therefore easy to execute. What else do we have in this datasheet here? Well, there seems to be a checksum in form of XOR bytes, UART parity, even again here, and here also mentioned the ACK is 0x79, so if everything works out we get this, and in case of an error we are getting an 0x1f back. Okay, let's have a look into the get command. So we need to send an 0x7f, which should be answered by 0x79. Afterwards we need to send 0x00 plus 0xff, which seems to be already the checksum byte because the command has only one byte. And if we do the math, so if we XOR 0x00 with 0xff, we get back 0xff. So the checksum riddle is here also solved. Okay. Afterwards, we should again get back an 0x7 followed by the version and the supported commands. So let's try this one out here. Okay, so now we've got the big picture about how to send or execute the get command, whatever you like to call it. Now we need to figure out how to set this chip into the bootloader mode and also where to connect our UART lines to. And those information might be in the datasheet of the chip itself, which we've got right here. The STM32F401 XB or XC datasheet. So let's try to answer the question how to enter the bootloader mode, and I therefore simply just press Ctrl F and we are searching for boot. Let's see. Awesome, boot modes. This sounds promising. At startup, boot pins are used to select one out of three boot options. Okay, boot from user flash, from system memory, or embedded SRAM. The bootloader is located in system memory. It used to reprogram the flash memory by using either USART1, which is PA9 and 10, or USART2, which is PD5 or 6. So one of them are our UART connections, and I would go with the first one with USART1, which means we are looking for PA9 and 10. But before we go to the pin description, let's see. The bootloader is located in system memory. Okay, we already got this. For more detailed information on the bootloader, refer to application note AN2606. All right, another data sheet. But first, let's have a look into the pinout description. Where do we find our UART connection? Okay, so we're looking for PA9 and 10, and therefore we are looking for pin. Yeah, okay. Pin description. Okay, let's go. Oh, pin outs and pin description. There we go. Okay, it's something like this always in those data sheets. So let's go to this one. This looks like an BGA overview, so not our chip. Here we've got it. So let's see if we can find PA9 and 10. Okay, here we've got it. And what we can do right now is we can take this pin out, or this pin description, place it as an overlay over our chip and then follow along these traces. Or we can simply take a look at these labels because it's already labeled correctly. Alright, so we've got our UART connection. Let's have a look into the other datasheet mentioned before, referring to the bootloader modes. And here we have it, the AN2606. I mean, searching for boot right now with Ctrl F doesn't make much sense anymore because most of it might be related to this keyword. So therefore we simply just scroll down a little bit. Okay, general information, related documents, general bootloader description. This sounds good. Let's click on it. Okay, bootloader activation, perfect. The bootloader is activated by applying one of these patterns described in table 2. Table 2 is here, and let's see. Okay, these are many patterns. So the first pattern is boot 0 pin is up and boot 1 pin is down. So I simply just suggest we try out pattern 1 and then we follow along. So we need to find boot pin 0 and boot pin 1 in our datasheet. And here we've got it. So we can see we've gotten boot 0 pin, but there is no boot 1 pin. Long story short, we simply tried out if it only works with one button. If we press the button while the board is running, no effect. There's also this reset button that could help us on our left-right combo. Okay, so we are pressing the reset button and we can see the blue LED turns off, but the board drains 0 amps, so nothing happens. We are permanently resetting the MCU. Okay, now let's press the reset button. Next the boot 0, then we release the reset button and then we release the boot 0 and the blue LED is off and we are draining 7 milliamps. The board must be now in the bootloader mode. Awesome! You can also use a power supply and just press the boot 0 button while turning it off and on again. This also works. Alright, let's bring in the Raspberry Pi Pico and start programming it to execute the bootloader UART commands. We therefore connect RX and TX and also attach ground. To see what's happening on the wire, we also attach a cheap logic analyzer. We turn it on and... oh nope, not the user code. Left-right combo. There we go, bootloader mode. After attaching the Raspberry Pi Pico, we are now draining 17 milliamps, and this is exactly what we want to have when we start interacting with the board. We will see later why it falls down to 7 milliamps after some interaction. But now for the start, we want to have 70 milliamps on a power supply voltage of 2.7 volt. Alrighty. And now we can finally start programming our Raspberry Pi Pico. So as an IDE, we choose Tony and we have to select our interpreter, so we can do this automatically, or we can set the DevTDY interface manually. Next, we switch to the MicroPython IDE, and this is absolutely awesome because now we can simply say from machine import pin to get access to all these pins. Pin 25 is the internal LED, so we set it as an output pin, and setting the value to 1, we turn this LED on. Awesome, right? Absolutely, but it gets even better because now we also have a live terminal. So we can copy and paste this code from top to the bottom, and now we can play around and toggle this pin live right here. Before we start sending our UART packages, let's start the pulse view, so our logic analyzer to observe what's going over the wire. We select the correct driver, scan for USB devices, there it is, awesome, and then we select our 2 channels because we haven't connected more. Next, we choose 2 gigasamples and bandwidth of 16 MHz. This is fast enough and records long enough for what we are doing right now. We start the trace and then we switch back to our MicroPython. Back to MicroPython, we simply import the UART library and then we define our UART interface. Basic baud rate 8 data bits, but parity. Parity needs to be set even, which can be done with parity equals 0. Then we've got one stop bit and the TX and RX pin. We try to import it into our live terminal and, oh, there's an error, and yes, because we haven't imported this UART library here. Now we can simply start sending our UART data, and we need to start with an 0x7f. We read it back and, oh, that's interesting. We get back an 0xFF and an Y, so 2 bytes. The Y is our 0x79. Y is simply just the ASCII representation, but XFF, that's a little bit awkward. Nevertheless, we got an acknowledge, let's see if it works out. We are now sending our get command, which means UART write, and our XFF as the XOR checksum byte. We read the data back and oh yes, we got it back and we can also see the acknowledge in front, the Y once again. Awesome. So right now we have no clue what these data mean, but I mean, we are sending the get command. So the first few bytes should be the version and the other one the supported commands. Let's get back to the datasheet. Yeah, this kind of fits, perfect. But I mean, we are not interested in the get command anyway, we just wanted to try it out that everything works. Speaking of everything, we have this strange byte at the front. So let's have a look into our trace what's going on here. Okay, back to Pulse View, we are now applying our UART decoder, also here basic UART settings, except the even parity bit. Okay, awesome. And we can see perfect. Exactly what we are expecting. We are sending 7F and we are receiving indeed 2 bytes, 0xFF and 0x79. Okay, so this tutorial is for beginners, and even if I cannot explain every single aspect in the given time, sorry for this, we should spend some time on UART, because this is a very crucial element in our glitching attack. So let's analyze the signal really quick. Okay, so 0x7f is what we are sending, and this seems to be correct, but anyway, let's do this real quick. We can see the line stays up and it drops down. This is our start condition for our UART signal. It's followed by 8 bits, and we can simply add those numbers together. So 0xf and 1 plus 2 plus 4 is 0x7. Little endian, so we're getting 0x7f. Then we've got this parity bit, it stays high, we count them, we can see, yep, it's an uneven number, so it needs to be even out, so parity bit is high, and then we've got one stop bit, perfect. This seems to fit. Okay, now let's see what we're receiving back. I also blend out the first package that we're not getting confused here. So we are focused on the top signal yet. Alright, so we can see, oh, no, the line is not high, it's low. This means we have to wait for the first drop, which happens just here. This is our start condition, so this is our start bit, and also here, followed by 8 data bits. Once again, we can simply count them together. In this case, we've got 1 plus 2 plus 4 plus 8, 2 times, which means we have 2 times 0xFF. Parity, it stays high, but we've got already an even number, so this parity bit is wrong. We already got an even parity, so this one should be low. And this is also why we get this PE. PE stands for parity error. And this already shows us a little bit of a problem. Nevertheless, let's finish the signal. We can see, okay, at the end it stays high, we've gotten stop. So this one is a UART package. Once again, we wait for the next drop. This is our start condition, followed by these 8 data bits. And once again, we count them together. Here we've got 1 and 8 sets, so this means 9. And on the right side, we've got 0x7. Once again, little endian, so we get back 0x79. Then we've got this parity and we count them. This time we've got an uneven number. We've got 5, so we need this parity bit to stay high to get an even number, 6. This matches, okay, perfect. And then we can see it finished with the stop signal being high also. Okay, the second package is correct. Okay, the last thing we need to talk about is the baud rate. And the baud rate is simply just the amount of symbols we can transfer within 1 second. So what is a symbol? A symbol is simply just one time unit, 1 bit. For example, the start bit here, this one here is 1 symbol. And this symbol here is 8.68 microsecond large. If we now want to calculate the baud rate, all we have to do is simply just to divide 1 by 0.0000868. So these are seconds. Let's see. Milli, micro. Okay, yeah, this is correct. And the result of this is round about 115,200. So this is the baud rate, the amount of symbols we can transfer in 1 second. Okay. If you want to get back from baud rate to symbol, that's also pretty easy. To get back the symbol, all we have to do is we have to divide 1 by 115,200. And this is round about 8, okay, not 8, 0.000000868 seconds. Okay? Okay. So these are the UART terms which are relevant during this video. Okay guys, I really don't want to bother you too much, but the UART communication is the bread and butter during our glitching attack, so I will sum this up now really quick, but it's also a very interesting issue and you might get or learn something out of this. So let's do this real quick. Okay, so we can see the 7F is correct, awesome, the 7.9 is correct, and the FF, this one here, that's an issue. Alright. We could identify it on the parity error bit, but having an odd parity wouldn't cause an issue here. Nevertheless, we know that this package is wrong, and we also know the reason why, because this line here, this one, this should be high. Not having this line high causes a very interesting side effect, because on the Pico side, this one here is the TX line, and this one here is the RX line. And we can see, yep, we are sending the 7F. So we're going low here. And then the first time we start sending a 1, it seems to be mirrored onto the other line here. And the other line is the TX line of the STM32. Let's pick a new color. Okay, let's choose blue. So blue is now the STM32 perspective. On the STM32 perspective, we're having a TX line here and an RX line here. So the STM32 is not actively sending a package, but based on the emission from the Pico here and also here, we are accidentally sneaking in an additional UART package, and we can see this UART package goes from here up to here. So this is our 0xFF, a ghost package which was never sent, but being caused by having those pins being next to each other on a breadboard, weak isolation of those cables, but most of all the main reason, not having this line high. So the question is now, who is responsible for keeping this line high? And the answer is simple. It's the UART TX interface. So if we take a look at this one here, this one is the TX side of the STM32. Because let's think about this real quick. This is very interesting. It's not an I2C where we're having a high impedance state, multiple participants on the same wire, dragging this line down and just releasing it for sending in 1. We are just having one participant, so the TX line is the only one that knows when this line needs to go up and down, because only the TX line knows when we want to send data. If we are now transferring this on the RX line, let's do this real quick. So let's transfer this on the RX line on the STM perspective. Okay, so we are here. Let's say the STM32 would keep the RX line high. Then the moment the Pico starts sending data, we wouldn't even recognize it because we are just keeping it actively high. So we can only keep the TX interface actively high because we know when the line needs to go up and down and up and down and so on. Alrighty? Okay, let's remove this here. So if the STM32, and I'm even unsure if this is on purpose or an issue, but if the STM32 would keep this line high, then this, let's call it baby interference here, wouldn't make it up to our wire because we would be actively stronger holding this line high. And therefore we wouldn't have the sneaked in 0xFF package on our UART line here. The question is now, is this a problem? And the answer is simple. We will find this out. Spoiler, it's not. So if this would be an issue, what we could do is we could apply a pull-up resistor here. So we simply tie a resistor up to 2.7 volt. And this resistor should be round about 2 or 10k ohms. So this would keep the line actively high until we would start sending. So at this moment in time, we are actively stronger and we wouldn't have this interference on our wire. What we could also try is twisting those cables, better isolate them. But nevertheless, we will see that this one is just an issue for the first package, and it also just causes an issue on our side on the Pico. So it's not on the STM32 side, it's just on our side. And we can simply say, well, let's ignore the first package, because if we take a look into the get command afterwards, we can see after having this first ghost byte, this line stays high and the rest applies correct. We can see 7.9 already high, and we can also see the data being transferred back. Everything is correct afterwards. So all we have to do is sacrifice one UART package and then we are good to go. Alrighty, back to the read memory command. Let's have a look into the datasheet. If you want to execute this command, we have to send 0x11 followed by 0xEE, which is already the XOR checksum byte. Then we have to apply 4 bytes of the address, so most significant first, okay? Then we have to apply another checksum, which is every address byte XORed against each other, okay? And then we have to provide the number we want to read. So in our case, we want to read all the time, the most we can. And last but not least, we also have to append here an XOR checksum byte of the bytes we want to read. Let's program this and let's execute this. Left-right combo, 70 milliamps, perfect, exactly what we want to have. Let's switch back to Tony. Okay, the 7F stays in place, but the get command needs to be replaced with the read memory command. Then we need to apply the address we want to read. So in our case, it's 08002080 followed by the CSC XOR checksum byte, which is every byte XORed with each other. Next, we need to apply the bytes we want to read. So FF followed by the checksum byte, which is FF XORed with FF, which means 0. And that's it. Let's also verify the A8 really quick. Whoa, that's really hard to tell. And why I have chosen this address? Because this is exactly the memory location containing our password. In a real attack world scenario, we need to start at the beginning and then we have to extract it one by one until we get the whole firmware. But here we want to have one glitch to get the password as a proof of concept, okay? Okay, looks good, let's execute it. And awesome, there we have it. Let's compare it with the original firmware. There you go. Okay, it perfectly matches. But I mean, the chip is not locked yet. Let's interpret this package. So we are sending in 7F and we are getting back an 7F79. So we are just printing out what we're receiving. Therefore, it seems like we are having another ghost byte on our wire. In this case, it's the 7F. But we know right now what causes this issue. And we also know that this isn't an issue for us right now. Okay, so we can move on. Afterwards, we're sending an 11EE, which is the read memory command. And this one will be acknowledged with an 79. And this is a very crucial aspect here. So the moment when we lock this chip, this command should be denied. Right now we get back in 79, which means we are allowed to read the memory. Awesome. Next we send the address with the corresponding checksum byte and once again we get in 79. Perfect. Afterwards we send the amount of bytes we want to read, 255 and 79 again. So this will be acknowledged and afterwards the data we've asked for will be returned. Everything works out as expected, but I mean the chip isn't locked yet, so this is something we address now. Okay, now we set the readout protection and we will verify if our script still works. It shouldn't be the case, so let's see. Let's attach our debugger, the breakout board, and then let's start the Cube programmer. Wow, it's been a while, right? So let's connect to our debugger. Here's the firmware, perfect. But this time we switch to option bytes and we set BB, which is readout protection 1. This means we get access to RAM, but the access to the firmware will be denied. So exactly what our read memory command tries to achieve. By the way, our glitch only just works for RDP1 to RDP0, because RDP2 doesn't even allow access to the bootloader we are in right now. So keep this in mind, please. Okay, so we have set the option byte, we disconnect and we try to connect back again and error data read failed. Awesome. This is exactly what we want to have. Access to the firmware is now being denied. So let's see if this still applies to our script. We unplug the debugger, pull out the board with those two little helpers to do it gently, put it back and here, please make sure that you align it correctly, otherwise you might short your board. And left-right combo, 70 milliamps, back to Tony. Okay, now let's execute and see what we get here. And, oh, okay, this is new. We might assume that this is because we have locked the chip, but nope. Look at this, we are neither getting 0x79 nor 0x1F, and we are just entering the bootloader, so this should still work. Only certain commands should be blocked, but we haven't sent any command yet, so time to investigate. Therefore we switch to SIGROC, where we've got the signal trace, and yep, there we go. Let's zoom in. Okay, once again, it seems like to be correlated to the issue with the low line, but this time it seems to be a little bit different. We can see we are ghost activating this line by sending a 1, okay, but then it doesn't look like that we are having a ghost package this time. If you take a look at this package here, or at these two packages, and overlay the 0x79 package, it looks pretty identical related to the amount of spaces, right? The only thing that's different seems to be the width, and this means the auto baud rate selection might have failed at this moment in time. Okay. Does this mean we're having another issue? Yes, it does. And this can happen to you very easily. So how to deal with it? Well, let's see. The auto baud rate calculation is being performed on the 7F package we are sending. The STM32 takes the pulse width and automatically calculates the baud rate. In our case, it should be a pulse width of round about 8.6 microseconds, which means we are having a baud rate of 115,200. The new issue occurs when we are connecting our Raspberry Pi Pico the first time to the board. The line is low, we are having some ghost package, and the STM32 seems to have some issues with the auto baud rate calculation. If we take a look into the signal, we can see it is a 0x79, but the baud rate, it's not 115,200, it's round about 52,000. If we apply this rate, we can see, yep, we get back a 0x79, which means access to the bootloader is granted. The problem now is we are sending with a different speed, so our command will not be interpreted correctly. And yeah, this sounds bad, right? Yeah, but only for the first package. I mean, afterwards we can see the line stays high and the auto baud calculation works. So what do we need to do? Nothing. We simply ignore this fact for the first package. The board will be reset anyway, and afterwards the line stays high, which means everything works out perfectly. We just lose the first package, which is absolutely nothing in a glitching attack where we perform dozens of attempts, okay? So we simply start our routine, and yes, the first package is lost, but afterwards we will keep glitching until we succeed. Alrighty? Okay. The next thing we need to address is the reset behavior, because we can see after executing everything once successful, if you rerun this code without resetting the board, we get an 1F, which means our command will be immediately denied. So this will never work out. We have to reset the board every time we are executing this command. And right now we have to do it manually. So let's have a look into how to automate this process, okay? Let's do this next. Okay, so we know that pressing the reset button will reset the MCU. The blue LED turns off and we are draining 0 amps. Now let's see how this button is connected to the reset pin of the MCU. To check this connection, we set the multimeter into continuity mode, which means we are injecting a very small amount of current into one probe, and if the other one picks it up, we hear this famous... There we go. Okay. So if we hear the sound, we know that those 2 points are electrically connected. Let's check the button. So one probe to the left and the right, and yep, we can hear this is connected. The top, yeah, so left and right on top is also connected. Awesome. So we're having 2 sides on this button here. Okay. Next we check if the button is connected to the N reset pin of the MCU. I mean, it has to be, right? But nevertheless, let's check it. Okay. So the top half is not connected. Let's check the bottom half. Yep, and there we have it. Okay, so now we are sure that the N reset button is connected to the reset line of the MCU. Let's check if this is also the case for the R label pin. We check against the button, nothing on top, but here we have it. This means it also has to be connected to the N reset line of the MCU. Let's check it. Yep, it is. Okay, let's sum this up here. We have 2 access points to the reset line of the MCU. One is the button and the other one is the R label pin. This means our life has become way easier because we can completely skip this button and get the states directly off this pin. And with states, I mean the voltage levels to copy them afterwards. And therefore, let's measure them with a multimeter. Let's go. Okay, here we have our multimeter set into voltage measure mode. We put the black probe into ground. We turn on the device. And now we are putting the red probe into the R label pin, and there we have it, 2.7 volt, awesome. The board is up and running, the blue LED shines bright, and we can see 3 amps are being drained. Now we are pressing the reset button. Let's do this in 3, 2, 1, bam, 0 volt. This makes absolutely sense because this is exactly what the N in front of this reset means. It means negative logic or active low. So by dragging this voltage level to 0, the reset line becomes active and we are resetting the MCU. Alrighty? Okay. Now we would assume that we simply take our Pico, set an output pin to high to keep the board active, and set it to low when we want to reset it, right? Yeah, absolutely. And this even might work, but it has a lot of traps. I do not want to get down the rabbit hole, and therefore let's keep it simple. We already have a high voltage on that pin, right? We measure 2.7 volt, and these most likely come from a pull-up resistor holding this line high, and this changes the way we communicate here. Let me simply give you an awesome demonstration about how the pull-up resistor and the communication here works. Let's do it. Here we have the reset line, and the tension of my fingers are the pull-up resistors, so they keep this line high. If we want to send in 0, we are actively pulling this line down, okay? And if we want to get back to a 1 or a high signal, all we have to do is we have to release this. So the tension of my fingers, the pull-up resistors, automatically snap it back to 1. Okay, let's simply make the connection and see how we can program it in the Pico. It's super easy, and therefore let's simply do it. Let's go. Making the connection is quite easy. We choose an arbitrary pin, in this case pin 16 on our Pico, and put a cable from there to the R-labeled pin. Now it's time for our left-right combo. We take a look into our logic analyzer trace, and we can see both lines are up. The moment we connect the Pico, both lines go down, and look at this. This time the board is resetting. Why? Because we have connected the reset line to our GPIO, and this line is also low. And we have just learned before, pulling this line to 0 will reset the board. So puzzle solved. Okay, now let's program it to get the board up and running. So we define our pin 16 as open drain mode, no pull up or pull down resistor, and the default value is 1. Keeping in mind, 1 doesn't mean we are actively putting a high signal on our output pin. It means we are disconnecting high impedance state and letting the pull-up resistor on the STM32 taking care of the pin getting high. Looks good, so let's copy this into our Python terminal, and the moment we do it, we can see the board comes up. And not just our UART lines are high right now, also the reset line, which is unfortunately not shown here, but otherwise it would still reset this board. So we know this line is also high right now. Okay. We can now play around with this value, and we can set it to 0, which resets the board, and setting it to 1 will get back the board active again. Okay, now let's write a small routine while keeping reset low for 200 milliseconds and getting it back up again for another at least 200 milliseconds. Afterwards we execute our memory read command and... okay, it fails. Yeah, because no one is holding boot 0 right now. Let's keep boot 0 pressed and see if we can execute this command multiple times. And awesome, 7F791F. This is exactly what we want to have. We can see we are successfully entering the bootloader, and our memory read command will be denied. This is working awesome. What's not working, or let's say at least nothing we want to do, is keep pressing the boot 0 button all the time. If you release it, we can see we are directly jumping into our user code again after executing this routine here. Okay, so let's automate this process next before we finally get to this glitch. Let's do it. If you're still watching, quite strong. So this is the last hurdle before we can finally start glitching. And unfortunately the boot pin is not being exposed. So what we could do is we could use a sense peak needle and directly place it on the pin of the MCU. But the glitch might need to run multiple days until the whole firmware is extracted. So therefore we choose a more reliable spot. This time we directly manipulate the button, and therefore we have to understand how it works. So once again, we get out the multimeter and put it into continuity mode. We check the bottom half of the button, connected. The top with the bottom, not connected, and the top half, connected. Okay, one recheck on top and bottom, not connected unless we press this button. Okay, let's check the voltage levels on the top and bottom rails. We put one probe back again into ground, and the other one, let's see. Bottom half, 0 volt, and they are connected with each other. Top half, 2.7 volt, also here. If we now press the button, the bottom half also gets 2.7 volt. Okay, to simulate a button press, we have to put 2.7 volt on the bottom half of this button. It doesn't matter if left or right, because both are connected with each other. Let's see how we can do this. Okay, this time we have to go down the rabbit hole because we do not have an exposed pin like the nReset pin before. I mean, yes, we could directly apply it to the MCU pin, but this setup is way too shaky. So let's understand how the button works and how to bypass it. Okay, we have seen the top half is connected with each other and also the bottom half. In the middle there's a switch, and in release mode this switch is open, which means the top and the bottom is not being connected. And this is the state when the button is not being pressed, the release mode. We have measured 2.7 volt on top and 0 volt on bottom, and we also have seen that the bottom half is connected with the boot 0 pin of the MCU. If this would be the circuit right now, it wouldn't work because the bottom half, where our boot 0 input is waiting for a signal, is not connected, and this means we have a floating line, a high impedance state. In this state we wouldn't get a clean 0 volt signal here. The signal line would be fluctuating and these would be recognized at random button presses. Okay, well, then let's connect the bottom line to ground, right? I mean, we have measured 0 volt, this has to be the way. Well, yeah, but this causes another problem. So let's do it anyway and see. If the bottom line is connected to ground, we get 0 volt here and it looks fine in the open state. But let's press the button and see what happens. If we press the button, we connect the top with the bottom half of the button, and I guess you can already see what happens next. If we directly connect the high side with the low side, if the top rail would be VCC, we would even get a short circuit here. So this does not work out in any way. Okay, what else can we do? Well, and let's connect the pull down resistor to the ground line. I mean, it works like a pull up, just the other way around. So let's see. The resistor has to be a large value, something like 10 kilo ohms. Okay. In the open state, we only have one path from ground to our button. It goes through the resistor, but that's the only path which is available, right? So we get a clean 0 volt signal on that input. Okay, now let's press the button. The switch closes, connecting the top and the bottom. Current flows down from top, and at this point the resistor is gigachat. We are not taking the path to ground, no, because we will always take the path of least resistance, and therefore we take the right path. I mean, literally. I mean, we are going directly to our boot 0 pin. Now we have a high signal line here, so we are entering the bootloader. If we release the button, the 0 volt provided by ground line takes over again, and because there is no other path with a less resistance, we get back our clean 0 volt. Low signal on the input. Now's the question where to apply our 2.7 volt to bypass this button press. Well, we could apply it directly on the bottom of this button. Right or left, it doesn't matter, because if we do it once again, if we are having our 2.7 volt on the bottom half, then it still doesn't flow into ground because of the pull down resistor, so we get our high signal on boot 0. And unless if we are not pressing the button, everything is fine. If we press the button, we have two different voltage sources and this could cause trouble. But I mean, that's the whole point of what we are doing right now, bypassing this button, so we should be absolutely fine. In this mode, we have a constant high signal on boot 0 without damaging anything. So we could now solder a wire, but I will use a SensePeak needle, and I choose the right side of this button because there's a little bit more space to work with. So let's do this. So here we have the SensePeak device. It's a spring-loaded needle and it's very sharp. So please take care of your hands, you can easily hurt yourself. We have two access points for a jumper wire which is connected to the needle. We place it on the right side of the button and connect our wire to pin 5 of the Pico, which is the 3.3 voltage rail. These needles stay in place extremely well, even if the table is a bit shaky. Next we power on this device and we can see 0 amps, which means the reset line is keeping the board low. Let's switch to the Pico. We take our reset line code and paste it into the terminal and voila! The device automatically enters the bootloader without pressing the button. We can now run our code and we can see it perfectly works out. Okay, the first package is for the trash, but afterwards it works. We can also add this into a while loop and then observe the ampere drain. We can see it sticks something between 6 and 9. This is very important because if the board crashes, it stays at a fixed value. As long as this value changes, we should be good to go. Okay, now we are finally entering the glitching phase. And all we need for this is a MOSFET and the Pico. Together, round about 20 euros. To figure out how the MOSFET works, I'm going to give you a quick example on the breadboard with an LED. Okay, but first, some theory. I know guys, I know, but we have to do this. A MOSFET is a fast switch with 3 pins: gate, drain and source. The gate is the control input. Applying a certain voltage between gate and source turns the switch on, allowing the current to flow from drain to source. Okay? Removing the voltage turns the switch off and blocks the current. So, a fast switch. Okay. There are different types, N-channel, P-channel, and a lot of things to consider. But we stick to this one type here, so the N-channel MOSFET. I have glitched all my chips with this MOSFET and so can you, okay? Alright. Okay, so now let's get back to the breadboard. Okay, we place our MOSFET onto the breadboard and connect the gate pin with the pin 16 of our Raspberry Pi Pico. Next, we take the source of the MOSFET and put it onto the long ground rail directly here. This one, of course, also needs to be connected to the ground of our Raspberry Pi Pico, otherwise it's just a floating line. Next, we place the LED into the middle, and here we have to take care about the positive and negative side. We connect the negative side to the drain pin of the MOSFET, which is the middle one. If we now apply a positive voltage to the MOSFET, the switch between source and drain closes and we have a ground on our LED side, which means current can flow. To make this work, we also need a positive side on our LED. So we take an 470 ohm resistor to not blow up this LED and connect it to the pin 5 of our Raspberry Pi Pico, which is the 3.3 voltage rail. This is now the big picture. If the output pin of the Raspberry Pi Pico is low, the negative side is not connected. If we apply a positive voltage, this connection gets closed and current can flow. To avoid floating lines, we also have to configure the Raspberry Pi Pico output pin with an pull-down resistor. Okay, let's program all of this real quick. First, we turn on the LED to see everything is up and running. Next, we define the pin 16 as an output pin, and we also need to apply the pull-down resistor here for the MOSFET, otherwise floating lines. Now, when we apply a 1 to this output pin, we can see the LED turns on. Awesome. And if we apply a 0, the LED turns off. Awesome. So this is what the MOSFET is doing. It's simply just a fast switch. We do not want to open a side quest here why we have to use the MOSFET and not the Raspberry Pi Pico output pin. There are a lot of circumstances for this reason here. Okay. If we want to turn this now into a glitcher, all we need to do is connecting the middle line of the MOSFET, which is basically ground, to the VCC line of our target. And you might think, what? And yeah. One method to create a voltage drop is simply shorting out this line. And this is exactly what we're going to do here. The short needs to be very short, of course, otherwise we are blowing up this device. We are talking about nanoseconds, maybe a few microseconds. Okay, let's stop here. So before we are doing a long explanation, let's rather do some cool demonstration, right? Absolutely. This way I can also order some really cool devices, but don't tell my wife, okay? Okay, so what we've got here is a freeze spray and a thermal camera. Isn't this absolutely awesome? It is. So with these two devices, I'm going to explain right now what a glitch does. So buckle up, this will be absolutely amazing. Okay, so here we have a small travel router, and on the backside of the PCB I have introduced our glitch. I swapped out one component to simulate it. Can you spot it? No? Let's get a close-up of this area here. Here we have it under the microscope. Do you see the C label? The component in place, it's not a capacitor, right? Yes, it is a resistor, a 1 ohm resistor. So this is basically a wire connecting VCC with ground, creating a short. Exactly what our MOSFET does when it becomes active, alright? Okay, so to demonstrate how the glitch creates a voltage drop on the main CPU, we cover the board with our eye spray. Now, the moment we apply power, the short, our glitch draws a large amount of current. Why? Because if we take this formula, I is equals voltage divided by resistance, and our resistance is nearly 0, we get a huge number, right? Absolutely. It is of course limited by our power supply and other factors, but it's still large. This means the resistor will get very hot because electrical power is converted into heat. So let's do this. 3, 2, 1, activate. You see this? The resistor melts first. This is exactly where our short corresponding glitch is. Amazing, right? Let's get another view under the thermal camera, which gives us an even better picture. Let's do this. 3, 2, 1. There we have it. And let's pause here, but just the video, not the device. So we power off this device, otherwise it will be completely fried. Okay, so let's sum this up once again. Why does this now cause a voltage drop on the CPU? So the power supply, PCB traces and the wire have all some resistance and impedance. According to V is equals R multiplied by I, the large current drawn by the short creates a voltage drop across the supply path, okay? So this simply means that less voltage remains on the CPU power pins. And this is exactly what we are going to abuse during our power glitching attack, okay? Alright. One important thing, if we arbitrarily short components like shown in this demo here, this doesn't work for a precise glitching attack. Our high current could be also downstream to other components. So therefore, do not short arbitrary components. This setup was explicitly modified and powered from a current limited power supply purely for demonstration purpose, okay? Okay, so this is what happens if we glitch, and therefore we need to make sure that our glitch is only a few nanoseconds or even microseconds long, alrighty? Okay, the thing that's missing right now is wait a certain amount of time and then activate the MOSFET for a certain amount of time. A simple version could look like this. Here we're using a delay and width and constantly increasing both until we hit our glitch. The exact values is something we have to figure out later with no oscilloscope, but once we have them, we can simply reuse them for this chip. So if you want to replicate this attack, you can simply copy my values. This should work for this board definitely. If we ran this code, we can see the LED starts blinking slow. And okay, maybe these values are probably too high. So let's reduce them for this demo here. Okay, now we can see the LED blinks faster and becomes longer active because the width, the pulse increases, which means the LED stays longer on, okay? So the longer the LED is on, the longer is our glitch. The final question is, where do we need to glitch? And we can find this answer in the datasheet. Yes, awesome, right? So let's pull this out. Okay. The power supply scheme page gives a very good overview about the power supply scheme. I mean, yeah, who could have guessed this, right? So here we have our CPU line, the point where we want to glitch, and we can trace it back to VCAP1 and VCAP2, this line here. They have direct access to the core rail. Nothing is in between, exactly what we want to have. We want to avoid things like the voltage regulator because this would interfere with our glitch, and by having direct access to the core line, nothing stands in our way. Awesome, right? Well, okay, I wanted a little bit too much because we can see we have some capacitors in our way. So we need to identify them and remove them on the board, but this is absolutely doable. Removing the voltage regulator, I guess this would be a problem. Okay, so let's check the datasheet for VCAP1 and here we have it. Pin 22 on our device. VCAP2 seems to be not available, which is perfect. We just got one here. Okay, let's check where pin 22 is. Directly here. VCAP1, awesome. Okay, let's try to identify VCAP1 on our board. How can we do this? Well, we simply take our CPU pinout label, put it on top, and follow along this green line here. This leads us to VCAP1, and here we have it. Perfect. Okay, we can also see the other VDD lines here have capacitors connected. These also interfere with our glitch because they are connected to the voltage rail itself. It might not be required, but removing them increases our chances of a successful glitch. Here we simply have to try out how many we can remove, because if we remove too many, the board becomes unstable and resets all the time. If we remove too less, maybe our glitch doesn't make it through. So I have done some extensive testing and I can say we can remove all three too, okay? So let's do this. The trick with removing capacitors is, yes, they are very tiny, but we simply grab them before they are hot, because then they are not floating around. You will get a feeling when this capacitor becomes loose, and there we have it, already lifted up. Awesome, right? So this is capacitor number 1, and let's get to 2, 3 and 4. Let's do this. Once again, we grab them, then apply our hot air, and we simply have to wait round about 30-40 seconds, and then we can simply take them away. Alright, looks good. Now we do a little bit of cleaning. We inspect all of them and This one here, this is not a short, it's not solder, we can simply scrape this away with our tweezer and then clean it again, and then we can see, yep, okay, those 2 points are physically disconnected right now. Alright. And this one here, this is the pin we want to attach our glitching line to, okay? Okay, so we have removed all capacitors and we also know where we need to place our glitch. So we can now start building our glitcher, or let's say I've already done this for you. We will go through the source code after the attack plan, but first I would like to show you one important thing. The MicroPython RP itself is way too slow. If we take the example code and run it through an oscilloscope, so the example code, how fast we can toggle a button, then we can see the smallest pulse we can get is round about 3 up to 5 microseconds. This is way too slow. If we port this code to C, we might get something like 1 microsecond, which is still way too slow. With the truly amazing PIO interface of the Pico, I mean Thomas Roth made a great video about explaining all these functionalities linked here, we can get a pulse timing or an interaction of round about 10 nanoseconds, and this is insanely fast and definitely more than enough. So what we're doing here is, yes, we are using the MicroPython RP, but we are doing the heavy lifting in the PIO world. Doing this in the PIO assembly language, we can get an insanely precise timing for our glitch. And this is what this code here does, okay? Perfect. Okay, we made it up to this point. The attack plan, let's have a look. The first thing we need to do is we need to have boot 0 pressed all the time. Okay, then we reset our board and then we send an 7F to perform the auto-boot calculation. We expect an 7.9 and then we send our read memory command. Directly after sending the read memory command, we perform our trigger. So let's inspect this part here. This is the glory of our glitch attack. Here we have it. Okay. So after the 11E, we have a delay window and we've got a glitch window. So let's see. We start by increasing the glitch window over time, and if we are not successful, then we get back to the delay, increasing this one. And also here, after increasing the delay, we slowly start increasing the glitch. And we perform this step over and over again. So this is our glitch. If we get back in 1F, we are resetting the board once again. And we repeat until we get in 7.9. If we have in 7.9 after our read memory command, we know that our glitch was successful and we can send our readout command afterwards, okay? So we have set up everything and all we have to do is wait for our successful glitch. Let's get into the final stage and let's execute this, okay? Let's go. Okay, here we are back at the breadboard and I've already connected the MOSFET for you. You will get a better angle in just a moment. We are now taking the drain line of the MOSFET, the black wire, and connect it to our sense peak needle. And you can also see I've attached a battery to the sense peak needle to get a better weight on it, which makes a better connection. Now, we need to make sure that we place the sense peak needle on the VCAP1 line, not the ground. Ground is directly next to it. So please don't mess up this connection, otherwise you will fry your board, okay? Okay. Next we take our VCC line and place it onto the boot 0 pin button to keep this button active. And last but not least, we do not have to forget about this. We need to change our TX line from the Python world to the PIO world. So from this pin to pin 17, okay? So here's a better angle. Here's the full picture. Now we power on this board and now we start glitching. Okay, let's go quickly over this. So we've got a reset pin and we've got a glitch pin. We also got a reset board routine, which takes the reset line down for 400 milliseconds and put it up for 400 milliseconds. So this simply just resets the board. Then we've got 3 PIO functions. So the first one is UART-TX implementation with an even parity, okay? The next one is also UART-TX implementation with an even parity, but this time we've got this line here. This one sets a pin high together with our stop bit. So the moment we are sending our stop bit, our UART signal is complete, we are triggering the glitch. And this gives us a very precise timing because this just takes 1 clock cycle, alright? Okay. So after the stop signal of our read memory command, we are triggering our glitch. And the glitch, that's the last one, the third function here. This function is, very easy. We are pulling the delay, we are pulling the width, then we are waiting the delay, then we are waiting the width, and then we are setting our glitch. Okay, so that's all. Then we've got a Python implementation for a parity bit. So it simply just counts the ones, and if it's even, then all good. If it's not even, we make it even. Then we have our 3 state machines. So the UARTX interface, the UARTX glitch interface, and also our glitch. Okay. And last but not least, we've got simply just the Python routine. So we've got our delay and width. Both are being put into the corresponding state machine. Then we are resetting the board, and then we are sending our routine 7F, 11, EE. And this moment we can see this is the UARTX glitch routine, which means after this EE, we are starting our glitch. And then we simply check if our glitch was successful. If this is the case, we are performing a standard readout of a hard-coded address. I mean, you can apply this dynamically, but for this demo here, I go with this address. The version I provide afterwards has a different address already set here, because that's an updated version that you can also interact with the UART interface. But this address here works for this demo here, okay? Okay. And that's it. This is the whole source code. Okay, the first thing we want to do is we want to get our board up and running. So we copy this code here with the reset function and paste it in our terminal. Now we run the reset function, and this makes sure our pins are set up. The reset has been successful, we have a clean state, and we can now finally start the glitching attack. We do not have to repeat this step, this needs to be done only once. Alright, so I have already predefined delays and width, and I would suggest let's simply run this. And here we have now both sides. On the left we've got our glitching code, and on the right the red line. This is our VCAP1 line, and you can see it's not really a line, it's going up and down because we have removed all these capacitors. So it's not flattened out anymore, which is great for us. Okay, what's not that great is the glitch. So we can see here, this is very weak. Yes, and the reason for this is the long jumper wire. So if you start glitching, my advice for you is take short wires. This is the best advice you can get if you start glitching. You will be also successful with this setup, but then you have to increase the width of the glitch to make it stronger. But increasing the glitch of your width also hits harder, which means it's more likely that your board gets damaged. So therefore, I will show you now a pro version that does require a little bit more advanced soldering, but it's not too advanced. So we can do this with a basic soldering iron, okay? So therefore, let's do a final adjustment to get really great glitches out of this board, okay? Let's do this. Okay, so the pro version is directly connecting a wire to the drain pin of our MOSFET, and we take a short, thin wire. You can see this here. Alrighty? Okay. Next, we place this wire directly on our pin, so there shouldn't be much room left to navigate around here, and we fix it with hot glue. This is very important because if you fiddle around with this cable afterwards, you might rip off your pin. So we need to remove the tension of this wire, and it also helps in placing it afterwards. Okay. Next, we take it under the microscope, and you can see there's a little bit of solder on the left side, but the moment we heat it up, all gets sucked up into this point. And you can also see I'm not using my special solder tip, so the thin one, I'm using the large one. So no excuses on this one that you have not the equipment to do this job, alright? Okay, next we clean everything up, and then we make sure that we're not having any connection between those pins. And yep, even from a visual perspective, we can tell no connection. Awesome. Okay, so this is the pro version of the setup, and this glitch is now very reliable and easy to execute. The soldering, yep, might be a little bit hard, but you simply just need a little bit of practice. You can do this. I fully believe in you on this point. Okay, then we insert our board, and here we need to make sure that we place it correctly. So if we are off by one, we are already in a huge mess here. We start the power supply. Our code is still in the terminal, so we can simply execute this function once again. Perfect, we have it up and running, and now let's switch to the oscilloscope. This time the line is blue, but it's still the same line, so it's just a different port of the oscilloscope. And we can see, okay, looks good, no glitches because we haven't started our glitching yet. Alright. This is now the final moment, and 1 hour video just coming to this point here, okay? Okay, so we adjust the values, and these are my secret values for exactly this setup. You will have success with these values and this setup, I'm pretty sure. So we take a delay, something around 20 and 50, and we take a width 1 to 16. We will narrow this down later, but I would like to show you something because we do not know the width of the glitch yet. So let's see how we could figure this out. Okay, so if we start the glitching, we can see the line goes up and down, it expands, but we cannot see our glitch, right? Right, so let's add a trigger point that we do not miss any glitches here. Okay, so the yellow point, this is now our trigger point, which means if the voltage drops underneath this point, so we have to think of this as a line, if we drop underneath this voltage level, we get a fresh update of the picture here. This way we can make sure that we are not missing any glitches because the picture might get updated simply too fast for us right now, okay? So as long as we are not dropping underneath this voltage level, the picture stays the same. And this is very important to note here. Having this trigger point right now, we can pay close attention to the width. So let's observe this and then let's see what's happening next. And awesome, now we have it. Here we can see our glitch. So we can see if the value is below 10, the picture doesn't get updated anymore, so it seems to be freezed, but this simply just means we are not dropping underneath this voltage level and the last picture was saved, okay? So having a glitch under 10 doesn't even have a real impact here. The reason why I have picked 15 as the maximum value, I mean we could go even larger, but if we go larger, then we have certain side effects. We program other option bytes, the board will reset, and we have more damage than it helps us right now. So we start low, and if we are not successful with this, we increase it in another run, okay? Okay, yes, we already got it. Awesome. We can read it here, right here, Stühler training. So this was the password in the protected firmware and we could extract it. Awesome, right? So this is real. You can do this too, and this is how you could extract firmware from a protected STM32F401 chip. Awesome, right? So the next thing we do is we have seen a width below 10 is useless. And I can tell you already that I've done thousands of glitches of this chip, and the width 14 and 15 works out very well for this setup here. So let's change it to this and let's rerun this. And here we have another one, success with glitch width 15, but this time we couldn't extract the firmware. This rarely happens. We get an accept on our read memory command with a successful glitch, but afterwards something seems to happen that we couldn't extract the firmware. Let's simply move on and see if we can get another one. And yep, again, here's another successful glitch. So you can see you can do this quite often with this setup. We could even further fine-tune this because the reset timing right now is very long. So we could reduce this by half, and let's see and run if we get another one. Bam! Okay, another one. So you can see you will be able to do this too. Believe me, if you follow along this video and the instructions made by me here, okay? Alright. So to double check that everything works as expected, we can see in the logic analyzer trace that our read memory command will be accepted after a successful glitch with 7.9. And if we take another trace, for example this one here, then we can see that our read memory command is being denied with an 1F. So this way we can make sure that the chip was locked and that our glitch was successful to extract the firmware. If you have watched this video until this point here, you are now able to perform a power glitching attack for the STM32F401 from RDP1 to RDP0. You are also able to replicate other glitches, you simply just might not be aware of it yet. So if you have any questions or require support, simply drop me a message in the comments here. And otherwise, I wish you good luck with your first successful glitches. Have fun!
Infinite cyber, infinite cyber.